Now we're going to see how to solve something like ax equals to b. If x was rational numbers, then we would be doing Gaussian elimination, and then you can easily see that Gaussian elimination does not work in this case, because if you solve the constraint as a rational numbers, you will get x as an answer which is non-integer. So you need a special procedure such that you can guarantee that if there is an integer solution exists, that procedure will find it. That procedure is called Hermite normal form. So let's see what is the value of Hermite normal form in the context of a equals to b. We will assume that a is a rational matrix and b is also a rational vector. They don't have to be integral. The thing is, you're looking for integral x, and so that is the difference. A and b themselves can be rational numbers. So what is a Hermite normal form? Hermite normal form is a lower triangular matrix. It assumes that the number of rows is smaller and the columns are wider. It doesn't have to be, but usually that's the situation. And this B is a lower triangular matrix, and all the entries in B are non-negative. Whatever number you see in the diagonal of matrix B are the maximum numbers. For example, if you see 3 here, you see 2, 1, and then if somewhere, let's say 4 shows up, then it's not in the form. So we can translate any matrix into a HNF form, and using the following 3 operations. First, we can exchange any 2 columns in your matrix. You can multiply any column by -1, or adding integral multiple of a column and add it to another. Let's see, for example, in this case you have this matrix, and you can obtain this matrix by, I suppose, swapping these 2 matrices. This matrix can be obtained by multiplying -1 to this column. Everything else remains the same. Look at this matrix. How did you obtain this? And if you think a bit, you will not find any way to synthesize it, but in a single operation. But you can obtain this one by, please try to solve this problem, how you get from here to here using single elementary unimodular column operations. So there's an important point to be made here. Why do we care about elementary operations? Because they preserve the satisfiability of a equals to b. It means is that if ax equals to b has an integral solution, and you apply this column exchanges, whatever all these 3 possible operations, the a prime x also will have a integral solution. It's very easy to see because by exchanging columns, it's basically variable roles are changed, so they remain integral. If you take a column and multiply with -1, the variable's role is changed. If the solution was 3, now the solution will be -3. So it preserves the integral. If you take a integral multiple of a vector and add in another, this same rule you just apply in the variables also, and you will again find a solution. If the solution is the new one, there will be solution with the original one, and vice versa. Not very difficult to see. However, please try to work it out yourself. These elementary operations can preserve integral satisfiability. So can we convert any matrix A into a HNF form? And once it's a lower triangular matrix, reading of a solution would not be that difficult, and we can see that how that can be done. So let's see, can we convert any matrix A, which is a full rank matrix? We can relax this requirement of being full rank, but for this presentation we will assume everything is full rank. And we apply a sequence of unimodular column operations, and we found an HNF form. So let's see how can we do that. To prove this theorem, I will simply present an algorithm. So without loss of generality, we assume A is an integral matrix. If A is not an integral matrix, we basically multiply by a constant on every number, and you get integral matrix. So that solves the problem. Okay. So our transformation proceeds in 2 phases. First, we turn into our matrix into a lower triangular matrix, and then we try to non-diagonal numbers to bring it within the range of the 0 and the diagonal entries. Let's see. So how do we transform something into triangular matrix? So it works from the top left to the down, and some point of time you have this matrix B, which is already lower triangular matrix, and this part is already set to 0, and C and D are yet to transform into our desired form. So we will work on D such that the top row has only first entry is non-zero, and everybody else becomes 0, and therefore we are progress in the size of growing lower triangular matrices. And to do that, we will only apply the elementary operations. Okay, so let's consider D is like this. Okay, D looks like this, and our goal is to turn this into a non-zero number, and everybody else in the top row should be 0. That's our objective. What do we do? First, we apply the elementary operation such that the top row becomes positive. Every number here is positive, but just multiply by -1 if any of them are negative. Now, what we do? We apply this GCD calculation. Record that in GCD calculation, what you do, you pick the small number and divide on everybody else such that they become smaller than this guy. That's exactly what we do. We pick some delta I, which is, say, it's a smaller small number, then let's say delta J. Then we just compute do the GCD operation. We subtract from delta J column delta J by delta I, and these many times. Okay, so this will look like a GCD operation, and once we keep applying this aggressively, eventually what will happen is that one of the column will have a top number non-negative, everybody else becomes 0, and then we exchange the columns, and the first column will become a non-negative number, and everybody else will become a 0. Now we ask ourselves, we have this lower triangular matrix P, and there may be more zeros sitting here which we don't care about. Let's suppose we have P looks like this. Now I want to make sure that all the numbers here are smaller than their diagonal entries and bigger than 0. Okay, so how do we do that? So how do we achieve this is by again applying the GCD-like operations. We take this column BII, and multiply this on this row on these columns in such a way that you bring the numbers between 0 to BII. Okay, which is very much like GCD-like operation. And then you will have an HNF formula. So let's look at an example which will make it extremely clear. You have this matrix and you want to convert it into the HNF form. So make the top row first. We'll first row triangular. So how to make a top row triangular? You need to do is that you need to take a GCD of the top guys. So if you do that, you take the first column and multiply 3 times and subtract it from the last column, and this guy becomes 0. Now what I do, 2 and 3, I again apply 1 time, subtract it, and it gets 2, 1, 0. Now this column has a small number, so what I can do is multiply by 2 times and subtract with this guy, and I obtain this matrix. Now I have one column which is non-zero, and everybody else become 0 in the top row. So what do? I just exchange the columns, and I obtain this is my B and this is my D, and we need to further convert this row into my lower triangular form. So how do I handle the middle row? I have to handle 4 and -9. So first I will do the top row positive. I multiply -1 by 1, -1, then it becomes 4 and 9. Now I have to apply again the 4 times. If multiply 4 by 2 times and subtract it, and it becomes 1. Okay. Now you have a 1 and 4. You multiply 4 times and you apply it here, it becomes 0. And now this guy has become positive. Now I will swap these columns. I will become 1, 0. the last column in this form, and so we are happy that this guy is positive and it's in lower triangular form. So therefore now we have reached the lower triangular matrices. But you can notice that these entries are not between the 0 and the top maximum value 1 and 9. So we need to convert them. First you need to -1 has to be brought up to 0. So multiply, just add this column and it makes it 0 here, and if you do that you get -2 here. Then you add 9 in each one of them, you get 7 and 7, and therefore you have now HNF.